Cool. Welcome everyone to the second episode of Let's Talk Manufacturing. This time we've got Gavin Baths here and we're talking about feeds and speeds. So yeah, we may as well get started. If you guys have got any questions, throw them in and we'll see if we can answer them. So feeds and speeds is a question that we get asked a lot. Is what are the best feeds and speeds for the machine? Every machines are different. Every machine is different. There's no set recipe for every machine in the world. There's no set calculation. A lot of it is based on trial and error, but there are some basic recipes that we can start from for most of it. Wouldn't that be right, Gavin?
I think that's a really good point, Brett. And I think it's more than just there's no one formula for one machine. There's no one formula for really any more than a couple of jobs. Tools vary a lot, material varies a lot, machines vary a lot. So I'm a firm believer that the best thing you can do to learn about feeds and speeds is to sort of learn the science and the maths behind it. To sort of get your starting point, and then there's nothing that really beats experience for sort of listening to a cut and getting a feel for what's a good cut and what's a not so good cut. So there's some obvious signs when you get it wrong. Things like smoke and heat and burning are bad, but there's a lot of also more subtle things that you can listen and look for. So hopefully today we'll go through as many of those as we can and sort of talk about some of the things that you should be looking for, some of the maths behind feeds and speeds, and give you a bit of a starting point for how to go about figuring these things out for yourself.
Yeah, no, that sounds really good. It's like I said, it's something we get asked a lot, and sometimes it's really hard just to give someone a set feed rate that they should be running at and a set RPM that they should be running at. You've got to always ask what's the material, what kind of cutter are you using, how many flutes does your cutter have, and these are all misconceptions and things that a lot of people don't fully understand. So it would be really good to cover some of these. So,
right. So I think, if you're happy to, start going through some examples and talking about some of the details, and then if you just want to interrupt at any time with questions, we can cover off the questions as they come in.
Absolutely. Thinking about the first thing, maybe we should go over, or maybe you should explain some of the language that's used, as in what is a feed rate and what and what is a rapid, because there is a big difference and a lot of people don't understand that as well. So,
sure. Okay. So the audience here will have varying levels of experience. So we'll start with the absolute basics, but I'm sure you're all very familiar with these things by now. We tend to call them tools or bits, cutting tools. There's obviously lots of different styles. I've got a few different ones here, which are for different types of work. You can see a 2-flute upcut end mill on the this one here. We've got a single flute upcut in the middle, and then we've got a chamfer mill as well. So different types of tools which will do different kinds of work and which will all have very different feed rate and spindle speed requirements. So really what we're talking about today is the speed that we're rotating the tool, as well as the feed rate as we're moving it through the material. Now there's different various different types of speed that we talk about, and we can express the feed in different ways as well. And there's a lot of, sort of terminology out there. When you're trying to learn this stuff, it can be quite confusing, especially because a lot of the information you'll find on the web will be in inches, and, many of you will be working in metric. So then you've got the added complexity of having to do all the calculations. But really, the way you can break it down is by rotating a round tool in material. The spindle RPM, or how fast that spindle is turning, is going to dictate how fast that cutting edge is actually traveling through the material. So even if that tool is not feeding, or it's not moving in a straight line, just having it rotating will be rubbing the surface of the material. So the first speed, I guess, that we talk about is what we call surface speed. And surface speed is how fast that cutter or the cutting edge is traveling through the material. And that's generally the easiest number to find when you're looking for a particular material. So if you can find a surface foot per minute, or SFM, that's the common one that a lot of tooling websites talk about. That's what the Americans use. Otherwise, you might have millimeters per minute or meters per minute, because it's typically quite a high number. So you imagine that tool spinning at 20,000 RPM, the little cutting edge is traveling through the wood or plastic or metal or whatever it might be at a pretty good rate of knots. So that surface speed is basically within a range. That's a given for a particular material and tool combination. So you might find a surface speed that is acceptable for carbide in aluminium, for example, and you might find another one for carbide in steel, and they will largely dictate your RPM. So you usually have a range that you can work within, but the first thing you want to be looking for is to try and find the surface speed that suits the material, and then set the RPM to suit. So that surface speed is often called VC. So if you're looking at tooling diagrams and you see VC, it's a V with a little subscript C. That's the cutting velocity. And then you'll also have another feed rate, which is the second one we're going to talk about, which is called VF. And that is the velocity of the feed. So that's how fast you're actually moving the tool along its path. So the spindle speed and surface speed is how fast the cutting edges are moving through the material. But then you can imagine if you start to move that tool along a path, it's now going to start taking chips. So it's going to take bites into the material as it moves along. And by changing how fast we move along, we can change how big those chips are. Now, if we go too fast, the chip is too big. It requires too much torque. The spindle can't generate it anymore, and we'll start to have problems, which can vary quite a lot, from chatter and vibration to breaking cutters. There's all sorts of things that can go wrong there. So those are the two main parameters when we talk about speeds and feeds. It's the spinning RPM speed and the moving feed. So Brett, do you think that's a fair starting point?
Yeah, that is definitely a fair starting point. I don't know whether this is a good time or not, but it would be good to talk about the difference between conventional and climb milling as well, because that is also a big factor for routers, especially so.
Sure. Okay. So as that tool rotates, most of the time we're not going to be doing what we call full slotting. So if we were to drive that tool down into the material and cut along with no basically engaging the full 180 degrees, the diameter of the cutter, the whole thing is cutting as it moves through the material. That's what we call full slotting, and that's typically the most load you can put on the tool. That's the most difficult cut that cutter can possibly do, full engagement. So in that scenario, it doesn't really matter which direction you go. It's always engaging the full cutter. But usually what we're doing is we're only cutting with a percentage of the width of the cutter. So if you imagine a block of material, I might just share my screen here and switch over to Fusion 360 for a minute to show you what I'm talking about. So just got a really basic example here. You can see we've got a couple of different tool paths here, which I'll get to the differences in a minute. But if we have a look at this tool path and simulate the movement of the cutter, you'll see that it engages a certain percentage. So I'll come around the backside so you can see. So it's not cutting with the full width. Now, because of this, we've actually got two options. We can cut in one direction or the other. And that's what Brett was referring to as climb or conventional. So because the tool is rotating clockwise, if you imagine it rolling along that surface and basically climbing its way along the surface, that would be climb milling, that direction. If we're cutting with the chips starting on this face and then being pushed outwards rather than sort of starting on the edge and being pulled through behind the cutter, we then have what we call conventional milling. Now, on manual mills, or I don't actually know with manual routers. I've only done very limited work with manual wood routers. Brett might know the answer to that one. I don't know whether people pay attention to the direction they cut. Brett, do you know if with a handheld router whether you
generally no, a lot of people don't, but that could also just be bad technique. Yeah.
Right. Okay. Well, we have to ask a woodworker, whether that's a thing or not. But generally, with CNC machines, anyway, or sorry, with manual machines where you turn handles to drive the axes, you usually avoid climb milling with any kind of significant load on the tool, because the tool can start to effectively drive the axis. It works almost like, the friction between the cutter and the tool will actually pull the table. And you can have it run away on you, and it's quite a scary thing. So generally, people will use conventional milling if they're milling manually, but with CNC machines, you tend to do the opposite and use climb milling where possible. So so that's the two directions that Brett's talking about here. We can choose. Now with a router, in a scenario where you've got a lot of material to remove, you imagine if it has to cut along in one direction and then retract, go all the way back before it can start the next cut, you're spending quite a lot of time, moving and not cutting. So one of the things we can do in Fusion 360 with one of the roughing strategies called adaptive clearing is we can turn on an option that's called, I've just got to remember where it is now, both ways. And if we turn on both ways, we can actually tell the software to calculate cutting passes in both directions. So you'll see if I simulate that one now, it will cut one way and then it'll actually cut back the other way. So it's cutting in both directions. Now, from a feeds and speeds point of view, the loads on the tool are different depending on whether you're climb milling or conventional milling. So you have to be a little bit careful that you don't set your feeds and speeds for one direction and then go the other direction at full pace and end up causing problems for yourself. So the toolpath gives you the option to basically set independent feed rates. So the spindle speed will be consistent, but you can see you've got this other way feed rate, and that allows you to specify two different feed rates. And actually two different step overs as well. They're the same in this case, but we'll talk about step over a little bit later. So I don't know. Does that answer your question, Brett?
Yes, certainly does. Certainly does.
So I guess the next thing, when we're trying to actually come up with numbers for those, the spindle RPM and the feed rate, as we were talking about, at the start, there's no silver bullet. There's no one number that's going to work for everything, of course. It really varies on what you're doing. So when you're setting those feeds and speeds, you also have to think about how you're going to attack the job. Now, I guess the broadest category of difference would be whether you're going to use more of the length of the tool and less of the diameter, or whether you're going to use less of the length of the tool and more of the diameter. Now, this will be a decision that you really make based on the machine, how rigid it is, the type of material you're cutting, and the type of tooling you're using. So if you have a very rigid machine and rigid tooling, and you've got the ability to go fast, then often you can use quite a lot of the length of the tool and take maybe a finer step over, and you can remove that material pretty quickly. We tend to find, and I'd be interested to hear Brett's view on this in a minute, but from our testing at ChipX, Scott and I both have the M2 Vertigo router in our garages, and most of our testing has suggested that we get better performance overall by taking a shallower depth of cut, so using less of the length of the tool, but using more of the width and then going faster. So we tend to find, most of the time in something like, I don't know, plywood, MDF, I do a bit with bamboo ply, I'm usually not taking more than 2 or 3 mil depth of cut, but I'll be using, maybe 80% of the diameter of the tool and going at 1500 to 2000 millimeters a minute. So that tends to be the formula that will sort of work for me, and we'll come back to those numbers in a minute. But maybe if you could just share some of your views on what's been working well for you guys with your machines.
Yeah, I mean, from my experience as well, personally, is I find with most things, you definitely get a more accurate cut, especially on a router. If you do take shallower passes and do them a little bit faster, I've always found that you're loading up the machine less. Matthew Mooney actually asked a question around that. He said, I was told router style milling prefer to have a full load on the cutter, like adaptive clearing, rather than say a contour cut with ramping where only the tip is cutting. Interesting. Yeah, I do understand where he's coming from with that. What are your thoughts?
So I think it really depends on the scenario. But okay, so one of the things with adaptive clearing, right? There is a detail where if you've got a very rigid tool holding setup, and there's not a lot of ability for the tool to be misaligned, angularly, then by having the tool running quite deep in the cut, the load is spread over, a large part of the flute, and your moment arm that's trying to rotate that spindle is less, so you can get a more stable cut, and you can obviously remove material a lot faster. In a smaller machine, or especially a desktop machine, just purely due to their size. I mean, the Vertigo is a pretty rigid machine for its size, but it's still not a rigid machine compared to a big cast iron, milling machine. You can have an issue that loading and deflection is actually pulling the bottom of the cutter away from the wall, so you can actually start to end up with tapered walls. So you really have to listen to the cut and hear how it's sounding. But generally, when it starts to go wrong, you can hear it. You can hear a pretty significant change. So I haven't personally had a lot of success with full depth cuts, but maybe I haven't gone small enough on the step over. I probably just need to do a bit more experimentation. But Matt, we'd be interested to hear your thoughts on that. If you've had some success with that, then great. It'd be quite keen to hear your formulas.
Cool. No, that'll make sense. What are some ways that you can what are some ways that you can cut, or some strategies you can use to reduce things like, or to increase accuracy and reduce things like backlash? Is that I've understand that there are different ways that you can set a toolpath up to be able to reduce backlash and increase accuracy on perhaps a less accurate machine.
I mean, I guess I don't know, from a CAM point of view, specifically for backlash reduction. Backlash tends, if you do have a reasonably small amount of backlash, the compensation and the software that controls the machine can definitely help a lot there, so that every time the tool changes direction, the software is compensating for the backlash. So knowing what your backlash is useful for a start, so that it can be built into the compensation and the control. But as for the CAM itself, I mean, not backlash specifically, but in terms of accuracy, what you do want to always be doing is taking a finishing cut. Yes. Because any loading or misalignment, so there's a few things that go into it, but that that deflection on the cutter is one thing I'm talking about. There's also deflection in the material. So when you take a heavy roughing cut and you push the material away to cut it, it does tend to spring back a little bit after the cutter moves past. So from a roughing cut, the amount of sort of force or pressure you've exerted on that surface means that you're not going to end up with a very accurate position of that wall once the cutter moves past. So you tend to want to rough your material out and then come back typically at a slower feed rate to finish off that wall or that floor, but taking a much lighter step over. And so you're just tickling the surface, removing a small amount of material, and then you'll get a much more accurate finished position. So that would be the one thing, would be taking a finishing cut.
So
and, yeah, sorry.
No, that's all right. So something I was asked the other day, someone actually asked me, is in theory then we were talking about climb versus conventional before. In theory, if you were doing a climb cut, that'd keep constant load on. If you're climb cutting, it would keep constant load on the machine, so you'd have less chance of backlash. Would that be?
It's an interesting idea. I mean, I know that with manual mills that tend to have a lot more backlash, that's one of the reasons they avoid climb milling.
Yes.
So, in CNC, where you tend to typically have a lot less backlash, then climb is a lot more stable. But I mean, my understanding of and from experience, I've had a manual mill run away from me climb cutting, and it's a pretty scary thing when the handle starts spinning and you're not turning it. But that's not specifically a backlash problem. But I believe, I don't quite understand why, but I do believe the backlash does come into why they don't use climb milling for manual mills.
Okay.
Yeah, sorry, I don't know all the details there.
No, that's right.
Yeah, so I doubt you would get with CNC and the appropriate feeds and speeds, I doubt you would get a significant difference in accuracy between climb and conventional. It's more about the performance of the cutter, and there's quite a lot that goes into it. If you want to Google chip thinning is an interesting concept, and the basic idea is that when you are running a cutting edge through the material, you can basically start by taking a bite, quite a thick bite. I sometimes think of it like a digger bucket, the digger bucket biting into the dirt over and over again. If you're taking a chunk out of that wall and you're pulling the cutter underneath below you, if you imagine the shape, or Google chip thinning, and you'll see some good diagrams. You'll see that the chip tends to go from a thicker chip to a thinner chip when you're climb cutting. Conventional tends to go the other way, so it starts thin and it'll break out to be a thicker chip on exit. Now the problem with that is that can shock the edge on the cutter as it goes from cutting. It's getting thicker and thicker and thicker, and then the chip snaps away, and that can shock the edge and basically cause more tool wear. Whereas chip thinning, where it's taking that initial big cut and then bleeding away to nothing, that's a more efficient way to remove the material. So chip formation and chip thinning, all those sorts of things, there's a huge science around those. And if it's the kind of thing that interests you, there's some amazing videos out there of ultra slow motion, under a microscope, watching chip formation, and the material, even materials which are quite hard, the way they behave on that micro scale when a cutting tool is moving through them is just amazing. So yeah, definitely go and check some of those out.
Maybe I'll link to some of those videos. I have got a list of them, so maybe I'll link to some of them in the description later on as well.
Yeah,
so
cool.
Now Stupid Robot Fighting League has just asked, what's the smallest cutter I can use in Perspex? I can probably answer that. Well, I don't think there's a size limit to cutting in Perspex. And there's not a size limit with cutting in any material, to be honest. It's really just about making sure you get your feeds and speeds right. And quite often with small tools, it becomes even more important. Really, wouldn't it, Gavin?
I mean, that's a great question. And the reason I like that question is it raises a really important point. We were talking about surface speed before. Now, that surface speed is basically how fast, just to recap, how fast that cutting edge is traveling through the material. Now, obviously, the smaller the diameter, the smaller your circumference of the cutting path. So you imagine if you take it to the extreme and you go to an absolutely, or pretty close to a sharp point, because you have almost no circumference, it doesn't really matter how fast you spin it. If you take it to the extreme, and it is just a hypothetical thing, if you imagine that point is actually 0 millimeters diameter, completely zero, then it doesn't matter how fast you spin it, it's not actually moving, because a point that's 0 diameter can't be turning. So obviously the actual speed that the metal is moving through the material that you're cutting is based on the diameter, and the larger the diameter, the faster the surface speed. So when you start getting down to small tools, you have to be spinning them really, really fast. So, I mean, I tend to find on 6mm cutters, I don't know what the exact RPM is on the Makita router that I'm using, because it doesn't have a RPM output, but I'd imagine I'm probably in the between 5 and 10,000 RPM range most of the time with a 6mm cutter. If I'm going down to some fine engraving with a sharp point, I can't spin that thing fast enough, because the surface speeds become so low when you're doing shallow engraving. So with small tools, in something like Perspex, there's a number of things you have to think about. If you're going down in diameter, the stability of that tool then becomes a problem, so stopping it from breaking gets difficult. But RPM is the other problem, and you need to be spinning those really, really fast to cut effectively. There is another factor, which is if you have what we call run out, where the tool is not spinning on its axis, but now it's starting to wobble as it rotates round, then that can be a real problem for tiny tools as well, because it's imparting loads on the cutter that can snap them. So for precise machining of very tiny details, and if you look at the likes of a company called Kern, Kern, or maybe Datron, or some of those guys that are doing a good job of really small machining, those spindle speeds are incredibly high, and their tool holding setups are very, very precise. But then they're in a totally different game in terms of budget. Those are not machines that many people can afford to have in their garage. So there's always a bit of a compromise, but you should be able to practically get down to tools that are 1 millimeter in diameter and cut things like Perspex successfully. I used to machine in a previous life electronic instrument panels, so backlit instrument panels for aircraft, and though the grooves in the back of those, we would go down to 0.8 of a millimeter, and they would sometimes be sort of 3 mil deep in acrylic. So cutting conditions, I guess you could sort of equate those to Perspex. And yeah, as long as you you keep the RPM up, and you manage your feed rates, and you get a formula that works for you, you should be able to come up with something that'll work successfully. Cooling can be quite a difficult thing with plastics, especially if the chips are getting recut and start to melt, and they sort of ball up on the tool, and can be a bit of a nightmare. But a lot of people have success with mist coolants and single flute cutting tools for plastics.
Air is a great way to cool plastic from experience.
Right.
With plastics, I've also found doing a very similar thing that you would do with aluminium, where you cut shallower, but you're cutting a lot faster as well, and it just breaks the chips off, keeps them a bit cooler, and everything's going a bit faster.
They're a lot easier to evacuate when they're really small as well. If you've got a long chip, it's difficult for it to actually get up and out of the cut if it's a narrow cut that's quite deep. So yeah, that's a good tip.
Good. Now Leslie has just asked a good question, and this is something that we get asked a lot. It's for more particulars, it can be quite hard sometimes. He's asked, what is the best depth of cut tool feed and speed for cutting 18mm pine plywood using an MX3? And I mean, I could tell you from my experience what I think is best, but I don't cut ply or pine as much as you do. So ultimately, what you come up with is always going to be better than what I come up with, because you're always going to be modifying those feeds and speeds. I've also found that if you use treated plywood, for instance, treated plywood is a little bit harder. Treated plywood has got more, seems to have a bit more moisture in it as well. So you've got to slow things down a little bit more. So in my experience, if you want a rough estimate of where you'd start, with plywood, I generally use a down cut, a single flute down cut. 18 millimeters, I'll do that at sort of about 4 to 5 millimeter step downs. And I'd be cutting at about 2 meters a minute. With the router set to about 4 on the dial, and 4 is about 22,000 RPM from memory. So that seems to work really well from my experience. But I don't have a lot of experience with different kinds of pine plywood. There are lots of different types, and I think that's a really good sort of starting point. Most materials, even MDF and things, I always find a good sort of medium recipe is always usually a down cut, about 2,000 millimeters a minute, and about a number 3 or 4 on the dial. Again, that's between sort of 16 and 22,000 RPM. That seems to be pretty consistent. Again, for between 4 and 6 millimeter step downs, I've found with treated plywood, you quite often have to do shallower step downs because it does seem to be a little bit harder, and there's a bit more moisture in it as well and makes the material a bit denser. So that causes issues. When you're cutting things like aluminium, generally you want to cut keep it nice and shallow. We've had really good luck in doing things like 0.2, 0.3 millimeter step downs, but doing 2.5, 3 meters a minute. That again seems to be really good for us. Now, there's no science in what I've just told you, so you can take a calculation, and I'm sure Gavin could probably talk a little bit more about how feeds and speeds are calculated. But the calculation is never going to be precise, because that's calculating based on the best possible scenarios with nothing stopping you from hitting those points.
Yeah, cool. Why don't we have a look at that? So, we also get this question a lot about what's the right set of parameters for a certain scenario, and where I usually suggest people start is grab a feeds and speeds calculator. The one that I've had some success with is this one, FS Wizard, and there's a free version. One is a Chrome extension, but there's also an app for iOS or Android. So if you Google FS Wizard, we'll get Brett to put a link in the comments. This is a pretty good starting point. So you basically have a material box up the top where you can choose the material that you're cutting. So I've picked wood up the top. I'll just open Fusion here so we can put it into a context in a second. Then we're going to choose the tool type. So for this scenario, I'm using an end mill with square corners on the bottom. You can see there's a number of different types of cutters there, but we're starting with a solid end mill. I've chosen carbide. With plywood, there can be abrasive materials in the resins, or in the I think that's what they call it, but what they bond the material together with, that can be quite hard. So things like bamboo ply, pine plywood to a point, and also MDF can be quite abrasive on high-speed steel tooling. Well, on any tooling, but high-speed steel being softer than carbide, you'll tend to find you'll wear tools faster. So at least most of the people I know run carbide tooling in ply for that reason. You can see here I've selected no coating. These are, well, at least the cutters that I deal with most of the time for wood are uncoated. You set the parameter or the parameters for that tool. So we've chosen the diameter, and if you've been using Fusion 360, as I know a lot of Brett's or Vertigo's customers do, you'll be seeing the same sorts of numbers in here that you put into your tool library. So the tip diameter, which in this case is the whole flute diameter, sorry, the same diameter for the whole flute. The number of flutes. Now this is important because when we're calculating how big a chip each tooth is taking, we obviously need to know how many flutes there are, because a cutter with twice the number of flutes for the same distance traveled is going to take twice the number of chips, and so those chips are going to be smaller. They're going to be thinner. So if a single flute cutter is taking a 0.1 mil chip, if you think of that digger bucket again, every time it takes a bite, 0.1 of a mil, if we go and change that to a 2 flute at the same RPM, traveling at the same feed rate, we're now going to be taking 2.05 mil chips for the same distance traveled. So you need to factor that in. How far the tool's sticking out and how long the flute length is. Now, the reason the calculator needs these is if the tool is sticking out further, obviously it's not as rigid, so it's going to back the calculation off a bit. We've got some options in there for corner radiuses, corner radii. There's not in this case. Helix angles and a shank diameter. So we put in all the parameters for the tool. We then decide where we're going to start in terms of depth of cut and width of cut. Now, depth of cut and width of cut have got various names depending on who you ask. Some people call it the radial depth of cut versus the axial depth of cut. I think about it as depth of cut versus width of cut. But basically what we're talking about there is how much of the length of the tool you're using and how much of the diameter of the tool you're using. So obviously, if you increase either of those numbers, radial depth of cut or axial depth of cut, if you can go the same speed, you're going to remove the material faster because more of the tool is doing the cutting. But you can't always just keep increasing that because eventually you'll break the tool. So it's all about finding the right balance. So what we're saying is, at least in our experience for desktop routers, we tend to prefer a shallower depth of cut but a higher width of cut. And those also, if you look at tool manufacturers' websites, they often call them AE or AP. And AE is the radial, the width of the cut, and AP is the depth of the cut. So if you think about what those numbers are actually telling you, then wherever you're getting your information from, you should be able to correlate those with some of the parameters that they're showing you. We've then got a couple of options as to whether we're chip thinning or using high-speed machining. Now, because we're using adaptive clearing in this case, I've turned on the HSM tab, which changes the calculation to allow for constant load. So that's what adaptive clearing gives you. It maintains constant load on the tool wherever it is in the cut. And then you have got some overrides down the bottom if you want to fiddle with things. So, excuse me, sorry. So what you'll see now is it's given me, as one of the inputs, we've got the maximum RPM, and now you can see up the top, we've got an RPM, we've got a feed rate, we've got a VC and an FZ. So the FZ is the chip load. That's basically the size or the thickness of that byte, and the VC is the surface speed, or how fast the cutting edge is traveling through that material. So for wood and carbide, I don't know, because I don't cut a lot of wood. I don't know off the top of my head whether it's 618.1 feet per minute is a reasonable sort of surface speed or not. So it's at this point that I'd go and start Googling and just check that that's in the right sort of ballpark. If it was in meters per minute, I'd probably have a better feel. You know, we might be totally off the top of my head, we might be in the 50 to 100 meter a minute range. I don't really know. So we'll have a look at that in a minute, because Fusion will give us that number. 10,000 RPM, I'm expecting at 10,000 RPM, that sounds pretty fast. I'm expecting we've probably got a pretty high feed rate, and 234 inches a minute doesn't mean much to me. So I'd be going off and doing 234 times 25.4. So it's about 6 meters a minute. So that's really quite a fast cut. From experience, I don't think, you know, maybe on a milling machine that's very rigid, this might work. I think we're going to have to be bringing that right back to, you know, maybe 2 or 3 meters a minute. So we'll bring this override down. So now we've got, where are we? 70. Let's have a look at that. I'll just do this by feel.
Matthew said you might be able to click on the menu and change it from imperial to metric. Yeah, I had a go at that. What you'll notice is that these numbers here are in metric because I set metric, but for some reason it still seems to give me the imperial output up the top. And I went and had a look in settings, but I couldn't find anything that seemed to be the right thing.
But it was a good
Right.
suggestion. It was a good
Yep.
suggestion. If anyone knows how to do that, I'd be keen to know. Um, okay, so I guess what I'm saying here is I've backed the override right off now to 30%. So once you get a feel for that sort of range, you'll find that when you start to put in different numbers for, you know, cutting diameters or materials, you probably are going to be able to use this as a guide and say, well, I know I can run at sort of 30 to 40% of the feed rates that this calculator gives me, and it'll give you a bit of a benchmark to start with. As I said before, I'm typically running the Makita at sort of between 5 and 10,000 most of the time for a cutter of that size. So I might choose to back this off as well. And then that's going to obviously change my feed rate to suit. So yeah, this as I say is a starting point. You can't beat the experience and the listening to the cut. And I mean, I often sit there next to the machine as it starts a cut if it's something that I haven't cut before, and I'll have my finger on the speed dial and basically adjust it as I go until it sounds right. So if it, if it sounds like it's screaming and vibrating and things don't sound good, I'll back it off and see what happens. If I start to back it off too much and it feels like things are loading up, I'll speed it up a bit, and you can sort of get a feel for, for where it sits nicely.
Also,
and yeah, you'll probably break a few cutters till you get the hang of it, but.
Yeah. Also looking at what's coming off the tool as well, and looking to see if it's really fine dust or if you're actually creating little chips. So the little chips quite often look like I suppose fingernails in a way. Would that be a good description?
In materials like plastic and metals, yeah, absolutely. In timber, you tend to not see. Well, I mean, I suppose it depends how closely you look, but the shape is a bit harder to determine. But
it is.
I mean, you're spot on there. You definitely don't want powder or dust coming out of this thing. One, because it's a bit of a risk for a number of reasons. Breathing it in. Hopefully, you don't have any enclosed spaces problems. But I guess if your machine was in a cabinet and you had dust in the air, that could be an explosion risk. So you don't want that fine dust. You definitely want it to be. A lot of people, I suppose, would call it sawdust, but it's not from a saw.
No.
But yeah, you're dead right there, Brett. If the tool is not actually taking enough of a chip, then it's rubbing on the surface of the material. So it's basically depressing the material as it goes past, but it's not biting into it. And if it's not taking that chip, you just end up generating a lot of heat. It'll, if it's extreme enough, it'll reduce the life of your cutters. It can be a fire risk. There's a number of reasons why you don't want to have it rubbing. So going too slow can be just as bad as going too fast. So you do need to get it right. Yep. So don't just think, oh, I don't know what the RPM should be, so I'll just wind it to max and then it can't be too slow. That can actually cause you problems that are just as bad.
Very well said. Now, Leslie's come back and he's asked something. So he said, what's the difference between, say, a 3mm tool versus a 6mm tool when you're talking about feeds and speeds?
Okay, it's a great question. The 3mm tool is obviously not as rigid. So you have to factor in the fact that we try with our tools, we try to make them as rigid as we can by doing things like keeping the shank at full diameter, as to get it as close to the cutter as we can. So we've got this taper in here to try and improve stability rather than just necking it straight down to 3mm. So the rigidity thing is an issue. You can't push it as hard if it's not as large a diameter. But the biggest thing is that you have to spin it twice as fast. That surface speed that we talked about earlier is going to be half for a 3mm tool to what it is for a 6mm tool. Yep. So for the same for the same surface speed, which is the efficient cutting speed as that carbide moves through that wood, this one's going to need to do twice the RPM of this one.
Yeah.
Feed rate wise, you're probably going to have to back off the feed rate on the 3mm because the cutting loads, if you're really pushing things to the limit, this one's going to take a lot more abuse because it's thicker and more rigid. So that's your kind of rule of thumb. But a nice way to think about it is when you get a formula that works for the 6mm, which might be how much of a step down you can take, look at that step down as a percentage of the diameter of the tool. So Brett said he's had some success with 4 to 6 mil. So, if we pick 6 mil because it's the easy example, then that's a 6 mil diameter tool. He's doing 100% of the diameter as the depth of cut. So we'd call that a 1D cut. It's 1 times the diameter in depth. So the equivalent cut for the 3 mil is going to be a 3 mil deep cut. So we're basically saying, if 1D works well for that, 1D will probably work well for that as well. And then the feed rate will be the thing you adjust to suit. So that feed rate and knowing how big that chip is, have we got some more questions waiting, or is it a good time to jump back into Fusion?
No, great time to jump back in Fusion. I'm just reading through these. Apart from that, Stupid Robot Fighting League has said that he's been plugging ChipX lots on his YouTube channel. So
thanks, we appreciate it. So, I mean, just very briefly, this is not a ChipX chat, but just very briefly, if you're not familiar with our cutters, the concept is we got sick of having to find adapters. Can you still see my webcam, Brett, or when I'm sharing screen, does it disappear?
It disappears, so I just see myself.
Okay, so I'll bring myself back for a second.
That's right.
Okay, so the main thing is we got sick of needing adapters and changing out collets, and 1/4-inch tools don't work 6mm tools don't work properly in the 1/4-inch collets that come with most desktop routers and all that sort of hassle. So what we did is we came up with a range of router tooling for desktop routers that have a 1/4-inch shank to suit your Makita or your DeWalt router, and then we use metric cutting diameters because down in this part of the world, obviously that's more convenient. We want to think in millimeters. So all our tools, even the tiny little ones like the 3 mils, they all have a 1/4-inch shank, so you don't need to change any collets. So yeah, thanks for the plug, Brett, and Stupid Robot Fighting League, which I couldn't believe my eyes when I saw your videos for the first time. Scott Moyes, the other half of ChipX, he said to me, "Hey, check out this Stupid Robot Fighting League," and I didn't know what to expect, but that is a very, very cool pastime, I guess you call it, or sport, maybe sport. So
it'll be an Olympic sport. You watch it.
Awesome. So yeah, cheers for the plug. All right, I'll jump back to Fusion and show you what I was talking about there. So if you've created any kind of toolpaths in Fusion before, you'll notice that you've got, you select your tool at the top. Now the tool will have preset feeds and speeds as defaults. And once you've got your tool library dialed in and you got all your feeds and speeds right, you shouldn't need to change them in here most of the time because you'll have those defaults, pre-selected. But all these sorts of things we've been talking about, like spindle speed, the cutting feed rate, the feed per tooth, they're all in here. And a lot of them are calculated from other parameters you enter. So as an example, that the cutting speed of the tip of the tool moving through the material that we talked about before, which is sometimes called VC or surface speed, that's this one here. So you can see as I change the RPM, that surface speed will change. At 1,000 RPM, it's 18 meters a minute. At 10,000 RPM, it's 188 meters a minute. So it's very quick to see. You don't have to do the maths on a calculator, is basically what I'm saying. So if we know we need, 150 meters a minute, we can just put 150 into here, and that will tell us, and that will tell us what speed we need. So now we're at 8,000 RPM. Now you'll need to look up that, the guide to see which number on the Makita router or the DeWalt router is approximately 8,000 RPM, but that's a way you can get a feel for it.
Stop you there for a second, Gavin?
Sure.
Just so everyone knows, the minimum speed on the Makita is about 8,000 RPM, and then it goes up to about 32,000 RPM. And obviously with most air-cooled tools, not only the Makita, but spindles, the slower you go, the hotter the spindle is going to get. So if you can run higher RPMs, the spindle's just going to last longer, and you're going to be able to operate the machine for longer as well. So.
Okay. Oh, that's good to know. I didn't realize it couldn't go slower than that. I need to put a tacho on mine at some point and find out what speeds I'm actually doing. But that's good to know. So just in case you don't know, if you do find a table online and you look up you're working with a piece of macrocarpa and someone's kindly put the correct surface speed for carbide and macrocarpa on the web, and it's 433 feet per minute, you can type in feet per minute in Fusion as well, and it will do the calculation for you. So you don't have to know the meters per minute, but by default it will give you meters per minute if you're using metric settings. So at that 10,000 RPM, we've got that 188 meter a minute surface speed. Let's just, for argument's sake, say that that's appropriate. The next thing we've got to choose is the cutting feed rate. And the cutting feed rate determines the feed per tooth. But it's not just the cutting feed rate. The feed per tooth is a combination of the RPM and the feed rate. Because obviously, the faster you spin it, for the same linear distance that you travel, you're not taking as much of a chip. So imagine that that digger is taking as many bucketfuls as it can. If you make the digger move forward faster, each bucketful is going to have to be bigger. Otherwise, you're going to leave material behind. So that's probably a bit of a silly analogy, but whatever.
You're allowed to say that.
Okay, so so you'll notice here that if I drop this, at the moment our feed per tooth is sitting at 0.1 of a millimeter. You'll see that if I drop this spindle speed to half, 5,000, it's now 0.2, because the tool is not rotating as fast. Each one of those bytes is going to be bigger, and 0.2, depending on the tooling and the material and the rigidity of the machine and the rigidity of the work holding and all the other parameters, that feed per tooth might just simply be too much. Now, one thing that you need to think about is, even if the machine is rigid enough, if the spindle doesn't have enough torque to actually drive the tool through that cut, when you start to take that cut, the spindle is going to slow down. If the spindle's slowing down, the chip load is just going to get bigger, because it's now moving forward through the material, relatively speaking, faster than the spindle was previously turning. And so the problem is just going to get worse and worse. So you definitely don't want to be stalling the spindle. Otherwise, you're going to be, generating more of a problem. So that can be another factor. So, typically you might be in the sort of 0.5 to, in wood, you might be in the 0.5 to 0.1 mil feed per tooth sort of a range. And you'll just have to, get a feel for that yourself. So I think Brett was saying 10,000 and a cutting feed rate of 2 meters a minute. Yeah, feed rate of 0.1 per tooth, and that's on a which tool was that? That was tool 13. So that is a 2-flute end mill. Now, if we change that to a 1 1-flute end mill, now we've got 1 flute that has to do the same amount of work. So to maintain the same feed per tooth, we're going to have to either reduce the feed rate to half or increase the spindle speed to double. So hopefully that's starting to make sense. If this is all new to you, hopefully you're starting to see the sort of relationships there and the balance between them. But the point I'm trying to make is that when you've got the tool defined, as long as it's got the right diameter, the right number of teeth, you can play with these numbers in here and you can see the effect it's having on that chip load or that feed per tooth. So that feed per tooth is often called FZ when you look at the documentation for a particular cutting tool. FZ is that feed per tooth, and to calculate it, it's basically the feed rate, so how fast the cut is moving through the material, divided by the spindle RPM, multiplied by the I've got lost in my head, multiplied by the cutting speed, so how fast the cutting edge is traveling through the material.
Yeah.
So that formula is widely available online, but Fusion's doing that in the background for you to give you that feed per tooth, because it knows the surface speed, it knows the feed rate, and it knows the spindle RPM, so it can give you that number.
Cool. No, that all sounds really good. I might just answer a few questions quickly.
Go for it. Go for it.
So Leslie's just asked what ChipX tool would be best for what he's doing. So he's obviously cutting 18 mil plywood, pine plywood most of the time. I would say to answer that roughly would be, and if you're not too worried about edge finish and you're wanting to cut your parts out nice and fast, an upcut, especially if you're going to be finishing your edges with a bit of sandpaper, and you're not too worried about a little bit of chipping, an upcut is always the best way to go. The tool will just generally last a bit longer. It won't heat up as much, and you can get rid of chips a lot faster. Down cuts, if you're wanting to get a really fine finish, and again for plywood, I would be going for single flute. Single flute for most things on a router is always a good way to go. Yeah, what are your thoughts on that, Gavin?
Yeah, I mean, I think that's pretty fair. If you're cutting 18 mil ply, then you're obviously going to need something that's got enough of a flute to get all the way to the bottom. So even if you're only taking 4 to 6 mil step downs, you still need something that's got enough flute length to get to the bottom. So this one's not going to do. That's a 16 mil flute length. I'm pretty sure we don't even do this anymore. I think we've changed this now to a 20 mil flute length because so many people are cutting 18 mil ply. So I tend to agree with Brett. I tend to use a down cut myself more often with a small step down because it's not a deep channel. You don't tend to have much of a problem with chip clearance anyway. So that down cut can just keep that top surface nice and clean. The fact that the tool is imparting a bit of thrust on the top surface and pushing it down protects that top edge. And upcut can tend to splinter the edges and sort of break them out. So I tend to use the single flute down cut 20 mil flute length 6 mil tool, which if you have a look on our site, you can choose from the filters. So we could go to the down cuts. And we should have a single.
You might want to screen share there.
Oh, sorry, I thought I was screen sharing.
That's right. And for plastics and aluminium, upcuts are definitely the way to go, especially to try and keep heat down. With aluminium, it's a must. You could never use a down cut on aluminium. It wouldn't. If you did, it would melt the aluminium very fast, and I've seen it happen before, and there are plenty of people that give it a go. And plastics the same. You're just throwing more heat straight back down into the material. It might work for a longer period of time, but again, you're not really gaining anything by using a down cut in aluminium. The big point of a down cut is to reduce splintering or breakout on the top surface. So yeah.
So I just realized I was talking rubbish suggesting the down cut with the 20 mil flute length because I was confusing it with the 2 flute upcut. So that 20 mil flute length would give you enough depth. That's this one over here. So it's a 6 mil diameter, 1/4 inch shank, 2 flute with a 20 mil flute length. That's probably the one that I'd suggest.
Yep. Do you have a down cut and an up cut there? Stupid Robot Fighting League has just asked that question. What is the difference between an up and a down cut?
Yeah, cool. Cool. It's a great question. And I can show you that example here. So I'm hoping the camera is going to pick up on it. Now, Brett, just to test, is that logo the right way around or is that reversed?
No, that's right. Yep.
Okay, because in my picture, the logo is reversed. If you have a look at this tool, you've got your cutting edge. So you can see the point at the end of the flute there. How's that clarity? Can you see what I'm talking about there?
Yeah, I can. Yep.
Yeah. So as it rotates through the material, you can imagine the chip getting generated. Now, if you look at the flute, the spiral going up, you can see that the flute is leaning forward relative to the cutting edge. So as that rotates, it has the effect, the spiral has the effect of pushing the material down. So that's what we call a down cut. So it's still cutting a chip and the chip will still be ejected up the flute, but the pressure that's being exerted downwards on the material was in that direction. Yep. Whereas if you have a look at an upcut, you'll notice that from the cutting edge there, the flute is moving up on, on that angle relative to the cutting edge. And so that's now going to lift the material up. And the lifting effect is better for chip evacuation. It's pushing it up and out those flutes, but you have that disadvantage of it lifting that top surface. So hopefully that answers Lindsay's question. But if not, we can talk about it more.
Cool. Is there anything else that you had there that you wanted to go over?
Yeah, I mean, I think I'll share screen again just briefly. I was going to just show a detail in Fusion here. So I've created a couple of example toolpaths here, and don't look at any of the numbers in here. I've put no thought into the maths. It's really just some extremes to illustrate the differences. So I've called these two options, either high axial, low radial, or that one was supposed to be low axial, high radial. Hopefully you can see this. So what you'll notice is that the low axial, high radial, this is low axial depth of cut and high radial depth of cut. You can see that there's a number of step downs here. So we've got 1, 2, 3, 4, 5. We've got 6 step downs to remove the material. So that's 6 layers of cutting. But if you look at it from above, you'll see that the distance between the tool paths is quite high. I think it's 80% of the tool diameter. So that would be one strategy, would be not using a lot of depth of cut, but using more of a width of cut. Whereas the alternative would be to go high axial, so now we're using more of the length of the tool, but because of the loading on the tool, we can't afford to have as high a step over. So this is a much finer step over. So if you look at keeping the same feeds and speeds, I think 10,000 and 2,000. 10,000 and 2,000. Yes, we've got the same spindle RPM and the same feed rate, same cutting tool between those two tool paths. If we do a simulation, and this is not to say that this would be the correct time on the machine, but just as a comparison, HSM's telling us that would be 9 minutes and 24 seconds to rough it using the high axial, low radial strategy. If we go low axial, high radial, same feeds and speeds, and simulate that, 14:33. So I've just realized that's not a fair test because one's using both ways adaptive. So I'll just go and turn the both ways off. Where was it? 10,000, 2,000. Sorry, bear with me. Oh, maybe not. Oh, well, anyway. So you can see the comparison in time there between 9 and 14 minutes. Obviously, in that example, the high axial, low radial would be faster. But having said that, I haven't put correct numbers into either of those toolpaths. So that high axial, low radial, for all I know, I might have to halve the step over for it to actually work, which would make it, longer. So you can do a comparison, but you shouldn't be talking by taking multiple step downs and a wider width of cut, because that's what we find works better on the desktop machines. You shouldn't find a huge difference between doing it that way and doing it the way you will see in high-speed clearing. If you watch YouTube and you look at adaptive clearing on a high-speed milling machine where you're doing, maybe 8 to 10 meters a minute with full flute length depth of cut, on a machine that's very rigid, that's all well and good, but where you can't do that, you shouldn't find too much difference between the two different strategies here. And in softer materials, woods and plastics and things like that, the effect on tool wear is not going to be as significant either. So I tend to prefer the low axial, high radial on a desktop router, and on a milling machine, I would always go high axial, low radial, unless it was a really complicated material, like super duplex or something like that. Hopefully that sort of illustrates the two different approaches, Brett.
Yep, definitely does.
Cool.
Cool. Well, it's been a little bit longer than the last one, obviously, but there's a lot to go through with feeds and speeds, and there's probably a lot more we could cover. So I think moving forward, the best thing to do is if you guys have lots of questions in that, maybe leave the comments below or on Facebook, and maybe in the future we can revisit this subject and answer some of those questions a little bit more in detail. But yeah, no, I just wanted to thank everyone for coming along and watching the video. We're hoping to do these every Sunday. Maybe not as regular over Christmas, but heading into the new year, I'd like to do something every Sunday, just to try and spread a little bit more information and answer some questions and help people out. So thank you very much to Gavin for coming along and helping out with this video.
Thanks for the opportunity. It's great.
No worries at all. And again, thank you to all our customers and that support us and that. So cheers.
Cheers, Brett.